to look at a fairly simple situation with a magnetic field, let's let this flat object here represent a loop of wire. Okay, so we have wire looped, many loops of wire around here, just one loop, it doesn't matter. Whatever number of loops we have, we bring a magnet close to this object. Okay, so here's the loop and here's the magnet. Now the field of the magnet is acting straight down. Okay, when the magnet's like this, the field is coming out the ends, it's acting straight down here on this loop. If I rotate the magnet 180 degrees, the magnetic field has now reversed its direction. Okay, so where the magnetic field was down before, it's up now. Alternatively, of course, I can change the orientation of the loop with respect to the magnet by rotating the loop. Now I've drawn a square loop rather than a round one. Loops don't have to be round, they can be any shape, as long as they complete a circuit all the way around the loop. So let's say we have two wires coming in, much like the loop that you have on the kit. That light aluminum loop comes around like this, and the magnetic field is in this direction with respect to the loop. Now the orientation of the loop, if you can see, and this isn't real clearly labeled, okay, if we have an object representing the loop, like say this CD here, okay, we're going to arbitrarily say that some direction is up and another direction is down. Okay, so let's say we've got this pen through the center of this loop and it's up. That's called a normal vector. That's normal to the plane of the loop. Okay, as we can see, it's supposed to be perpendicular. It's a little hard to hold it there. Now, as the loop rotates, and let's rotate the loop, let's rotate it in this direction. As the loop rotates, the direction of that normal vector reverses. And if we continue rotating around till we come back to the original orientation, the loop, or the normal vector, has gone through a 360-degree rotation. Now we're going to use that normal vector to determine the orientation of the loop with respect to the magnetic field, and theta is going to be the angle between that normal vector, which I've labeled with a small n here. It's a little hard to see, it's poorly written. Magnetic field is down, normal vector is up, then theta is 180 degrees. Now as we rotate the loop, or as we change the direction of the magnetic field, in this case let's assume that we're rotating the loop, the magnetic field remains down, but the normal vector goes from up, as we rotate the loop, to down. And now the normal vector is coming out of the center of the loop and is pointing down and makes an angle of 0 degrees with respect to the magnetic field. Now if we continue rotating, we'll come back to this position again, where the loop, the normal vector, is now opposite again in direction to the magnetic field, and we have the 180-degree angle again. Now the flux through a loop can be understood by watching the shadow of a loop as it rotates. So I'm going to put a light on here, and going to use the CD for a loop. It's down here a little bit below. Okay, right now the CD is intercepting the light flux, so that the flux is